Now I know you've seen differentiation before, and we've talked a little bit in some other videos about how important differentiation is to machine learning in order to be able to compute gradients for optimization and things like that. But one of the things that can be a little tricky and a little challenging, particularly when you're getting started, is that a lot of the functions that we deal with in machine learning have either vector inputs or vector outputs, and sometimes they even have matrix inputs and matrix outputs. And you might reasonably wonder, how do you take derivatives of those kinds of things? Now, it can be kind of a complicated thing, but what I thought I'd do is take a few minutes to talk through a few examples and try to give you some sense of how it works so that it can be kind of demystified and you can think about how you might attack some problem that you encounter in machine learning. So we're going to talk about practical differentiation. Let's start with the most basic kind of function. Let's imagine that we have a function f and it takes in a real number and produces a real number. This is great, no problem. We know how to handle this. If I take the derivative df dx, then that's going to be a thing that takes in a real number and produces a real number. Right? It's just the slope of that function. On the other hand, one thing we might encounter now is to have something like f takes in a real number but produces a vector, say a vector in Rn. That's a little bit of a trickier thing. So maybe this would be something like f of x is a scalar x multiplied by some vector v. So it takes in just a scalar but produces a vector for its output. So what's the derivative going to be of this? Well, once we start talking about vector functions, now we need to start thinking about Jacobian matrices. So this kind of function is going to be something that also takes in a real number and produces a column vector Rn. Okay, what about things the other way around? What if we had a function f that takes in, say, Rm and produces a scalar? Now this is an important case because this kind of thing comes up quite a lot in machine learning problems where you have an optimization problem and this is an objective function that you're going to try to minimize. And when you get something like this, then we would talk about the gradient of f. And the gradient of f is going to be a function that takes in a point in Rm, but it's now going to produce a row vector in Rm because this is a Jacobian. So this was a column vector Jacobian because it had one input and n outputs, so we get a column vector. This gives us a gradient. It has m inputs, and so we get a function output that is m entries in a row. So just to be concrete, an example of this kind of function might be something like we take a vector x and maybe we just take the inner product of x with some vector, just to make it concrete. So you can see this would take in a vector, produces a scalar. Still more complicated would be a function that takes in a vector in Rm and produces a vector in Rn. Now here we need to think about the Jacobian. So let's write that with a j. So here the Jacobian is going to be a function that has the same inputs. So it has Rm for its input, but now it's going to produce a matrix, the Jacobian matrix, for all of those possible inputs. So that's going to be a matrix that is outputs by inputs, right? And we can kind of think about this that if we were to take one of the outputs, that should give us a row vector, right? Because it would be a gradient. And so if it's outputs by inputs, then we have n rows and m columns. To give you a simple example of the kind of function we're talking about here, this would be a function like, matrix m hitting a vector x, right? And so then we would expect this Jacobian to look like the matrix M. And things can even extend beyond this. We could wind up in a situation where we have say a function that takes in an M and produces a matrix. So we could have something that would then, maybe it outputs something that's M by n, for example. So now the Jacobian is a little bit of a weird thing because it's going to take in, again, a point in Rm, Now it's going to output a thing that we would call a tensor. So this might be a situation where we have a function that takes in a vector and maybe it produces the outer product of that vector with some other vector. So this takes in a vector and then produces a matrix. Let's talk some more about this object. So this is what I'm referring to as a tensor. And the way to think about it is we talked about things like column vectors. We've talked about things like row vectors. We've talked about things like matrices. Well, this is just sort of extending into another, I'm going to use the word dimension here, but that's obviously a loaded term. But instead of instead of these kind of vectors and then a square type thing, we get a cube type thing. So it is indexed by 3 indices. Part of the reason this is confusing is because it is absolutely tempting to refer to this as having 3 dimensions, because it kind of looks like a 3-dimensional physical object. But of course, dimension is something that is already loaded with meaning in linear algebra and other ways. And so it's a little bit more helpful to talk about, say, the order of this tensor or the degree of this tensor being 3. Sometimes somebody might say something like that's a 3 tensor. And then, just to keep you guessing, then they'll refer to a matrix as a 2 tensor. So in something like continuum mechanics, you'll see people refer to tensors all the time when they really, from our point of view, would mean matrices. Nevertheless, don't be super surprised if sometime you encounter somebody writing down a tensor and they talk about it being a 3-dimensional tensor, or even more confusing, a rank 3 tensor, which is really overloading the term rank in a way that we don't like. These are things that you can easily represent in NumPy. NumPy is very happy for you to add sort of additional dimensions to its shape and to kind of make this object bigger, and often that's a nice way to do different kinds of computation. There are some complexities in reasoning about bases and coordinates and things with tensors, and if you're a physicist, you're probably pretty upset with the way I'm talking about this. But from our point of view here, just think of these as generalizations of matrices. Instead of tables of numbers, I now have a sort of a 3-dimensional table of numbers. Now, I think it's worth taking a minute to try to extract the general rule that we're seeing here and write that down. So let's imagine that our original function has some shape for its input. And here I mean shape in the NumPy kind of sense. And it has an output that has a particular kind of shape. And I'm just going to generically say that we're going to have n for that shape. And this is going to produce some kind of object that has some output shape. Now the idea then is that we can think about the Jacobian of f as being a function that takes the same input but produces something that is output by input. Sometimes things are 1, and so that output is simple, but as the input and output shapes become more complex, then we start getting into this region here where we're thinking about higher order tensors. Generally speaking, taking the derivatives of these more complicated kinds of functions still obeys the same kind of rules that you're used to from scalar functions. For example, the derivative of a constant is still 0. Similarly, when you take the derivative of an object with respect to itself, then you get whatever the appropriate notion of identity is. Also, the derivative of a sum is still the sum of the derivatives. The derivative of a scalar multiple is the scalar multiple of the derivative. Where things get slightly more complicated is in the chain rule and product rule. And some of the reason for this is because you have to be careful with shapes, and some of it is because you have to be also careful with non-commutativity of some of these objects. Let's work a couple of examples to see how this kind of thing works, to see that it's really just a direct generalization of the kinds of things we already know. Let's start with a function that takes a scalar and produces a vector. Here's such a function. We'll take f of x, and we'll make it 3x plus 42, and say sine of x. Pretty simple. What we're going to do is just differentiate each of these parts of this vector, and we'll get what you'd expect. We would get df dx then is a vector that is going to be 3 and cosine x. So we just differentiated each piece of this as though it were a scalar function. Sometimes we do some notational shortcuts, and we might have a function, say, that looks like, maybe we have a function that looks like this, where we take x and we multiply it by some vector v. So this is a function that's taking a scalar x and outputting a vector. And so when we think about what would happen here, then this is sort of like saying we're going to write this as xv1, xv2, and so on. And so then, when we think about taking the derivative for each one of these, then what are we going to get? We'll get a new vector that has a v1 and then a v2, and so on. And so we could write this in our compact kind of notation as a vector v. And so we might say that the derivative of this function is just v. So these are examples of a function that's a scalar going to a vector. Now let's take a look at a function that is taking a vector and producing a scalar. Now a lot of it is going to look the same. So let's imagine that we have a function that's taking a vector. We'll say x1, x2, x3. We'll say it's x1 cubed plus x1, x2 plus 42, x3. We can do this almost exactly like we solved this problem, but we're going to focus on the inputs rather than the outputs, and we're going to get a row vector that is the gradient of this function. So we would write that as this one. This is called a nabla. F is going to give us a row vector. So first, I'm going to differentiate with respect to x1, and I'm going to get something that looks like 3x squared, x1 squared, plus x2 for my first entry. Then, in this row vector, the second entry is going to be the derivative with respect to x2, which here is just going to be x1. And then the third entry is going to be the derivative with respect to x3, which is just going to be 42. So I've done the same thing. I'm just applying this element-wise, and I'm getting a row vector because it's a gradient. Okay, so that's the straightforward way we might write everything out, but let's look at an example that's kind of comparable to this. So a function that we might have as a function here, I'm going to write as a vector x. We might have x transpose v for some arbitrary v. This is a function that takes a vector x in and produces a scalar. I could write this out if I wanted to try to think it through as a sum over the product, of course, of each of these components. And that can be kind of useful because, as we saw, the sum rule still applies. That is to say that the derivative of a sum is still the sum of the derivatives, and I can look at this and see that it must be the case that I get a bunch of vi's. So if I think about what I'm doing here, then I would say that the gradient of f is each of these individual guys. So with respect to x1, df with respect to x2, and so on. And of course, each of those individual terms in this sum, its derivative with respect to that x is just vi. And so what I see is that this will be, in this case, this is going to be a v1, a v2, and so on, which I could write just as v transpose. And the transpose is because this needs to be a row vector in order to be a gradient. The gradient case, that is where you have a vector going to a scalar, is a pretty important one. So let's work a couple more examples to get more of a feel of how this works. And let's start with a really important function, which is the squared norm of the vector x. So we'll say that f of x is our good old L2 norm squared of the vector x. And just to remind you, this is a sum over the elements of I of xi squared. And so probably right away, you can kind of see where we have to be going with this. If I take the gradient of that, then I'm just looking at each element by itself. I'm starting with x1, and then x2, and so on. And so if I write those guys out, then I'm going to get a row vector. Let's see, when I equals 1, then it's just going to be 2 x1 when I equals 2 to x2, and so on. This is just applying the scalar rules, but to each one in turn. And of course, I can see this is going to be 2x transpose, which is kind of looks like the scalar rule, right? We had that, we were kind of squaring things, and then we pulled down the 2, and we again get a row vector with that x transpose. All right, now let's add a little bit more to this. Now let's actually think about the norm itself rather than the squared norm. So now we're going to need a square root. Let's take a look. So let's make f of x equal just the norm of x with no square. Now this is square root of that sum. So of course, we could write it like this to get a little bit more of a handle on it. And of course, we can write this even a little bit more tightly if we're happy with inner products, where we could say x transpose x to the square root, to the 1/2. So now we have a scalar whose square root we're taking, and we'll apply the chain rule. It's going to be easy because with the scalar, we don't really have to worry about order. So we can make this into 1/2 x transpose x to the negative 1/2, just like we would if this was a scalar, and then chain rule gradient of x transpose x. Good news, this was x transpose x. So we know how to do this. We know then that this is going to be 1/2 x transpose x to the negative 1/2 multiplied by 2x transpose. This half and this 2 cancel, and we recognize that this is the same thing we started with, but now in the denominator of a fraction. And so we can see that this is x transpose divided by the norm of x. So this norm piece in the denominator is just this guy. And then, of course, we have that x transpose, and the 2 and the 1/2 cancel out. Okay, we're feeling good about that. Now let's look at a function that takes a vector into another vector. Let's say that we have f of x as before, but now what happens is we hit x with some matrix M. Now I find it kind of useful to think in terms of each of the outputs and then think about the gradient of that. And so if I was to say mx, and I wanted to talk about the ith entry of that, then that's going to be a sum over, let's say, j of mij multiplied by xj. Because I'm taking a row of m and I'm computing its inner product with x. And so once I think of it that way, the gradient of that thing is just going to be that row m. And so of course I need to do that though for every one of the i's. And so that's how I'm getting a Jacobian matrix. In this case, the Jacobian matrix of f is just going to be the matrix M. And again, you can kind of convince yourself of this by thinking about every output corresponds to a row of M, inner product with an X. And of course, as we saw just a second ago, that's a case where it would just be that row by itself that would kind of stick around as a gradient. And I'm doing that for every possible output, which is just producing M row by row. So the Jacobian matrix of this linear function is just the matrix M. This, by the way, shows us one of the kind of identities here, which would be if I had f of x equals x, then the Jacobian of that function is going to be the identity matrix. Because it's like M is identity here, right? It's like I'm hitting x with the identity matrix, and so I'm just getting that identity back. Now let's take a look at the example where we have a vector input and it's producing a matrix output. And let's write this as a capital F. In fact, I'm going to put 2 bars under it like that to make sure that we agree that this is a matrix that is constructed from a vector x. And we're going to choose something simple. We're going to do x multiplied by v transpose. Now let's think about what this is computing. So if we were to zero in on a particular value, so let's imagine that I said f of x and I wanted to ask about the ijth entry in this matrix, then if I think about what that's computing, then that is going to be xi vj from this equation. Now if I want to take the derivative of this object with respect to each of the entries in x, then now I'm getting an object in which I need a third index to describe what's going on. So if I said the partial derivative with respect to xk, let's say, then of this guy, then I'm looking for the partial derivative of this xi vj with respect to xk. So this is only going to be non-zero whenever k equals I. And in that case, it will multiply by vj. So this three-dimensional object will have kind of two cases. We'll have it be vj when I equals k, and then 0 otherwise. One way we can write this is to use something we sometimes call the Kronecker delta function. So this is a function that in this case we would write like this, and it is 1 when the indices are equal and 0 otherwise. And we would do something like this. So this is a kind of a third degree object, right? It has this cubic structure like I showed you a couple minutes ago. So if we were to try to write this out, we could tackle it by trying to write Jacobian of f of x, right? We could say, let's think of this as an array of matrices where each array is itself the sort of partial derivative with respect to that x. So this would be partial f, partial x1, partial f, partial x2, and so on. So it's like I'm making an array of matrices. And what this is going to give us, if we sort of think about this structure, is each of these is just going to slice out one of the VJs. So we'll wind up with something where we have like a V1, a V2, and so on, and then all zeros everywhere else. And then the next matrix will have zeros, and then V1, V2, and then zeros. And we'll be following that pattern for all of the inputs. And so you can see that we can think of this tensor as being just a table of numbers that has 3 dimensions and not just 2. Things like tensors make coming up with a general purpose product rule a little bit challenging, but it's useful to walk through a couple of examples to kind of see how it does generalize the thing you are familiar with from the scalar case. And to that end, let's imagine that what we wanted to do was to compute the gradient of two quantities, let's say V inner product W, where significantly we're going to imagine that we're taking the gradient of these guys with respect to some other variable x. Okay, so it's like V and W are functions of x, both of them depend on that value, and we need to compute the product rule for this inner product. So our starting point can be, of course, to write this out in terms of the sum. So let's do that. We'll write it as some VI WI. And we're taking x here to be a vector. So if we wanted this gradient, then just as before, we could write this out as the row vector that we're interested in. So let's do that. It would be partial of this sum, VI WI, with respect to x1, and partial VI WI with respect to x2, and so on. So nothing surprising here. It's just the gradient as we defined it. It's the row that is the derivative of this quantity with respect to each of the variables in x. So these are just scalars. We can just turn the crank on this and think about what is the derivative of this sum, VI WI, with respect to any given, let's say, xj. Well, no big deal. This is just going to be the product rule. It's going to be the sum over I of VI partial WI partial xj plus partial VI with respect to xj multiplied by WI. So nothing fancy here. I'm just applying the scalar rules. But notice that I can apply the distributive rule and push these sums within each of these. And when I do that, I realize that I'm just taking the inner product between these guys and the gradients. So far, so good. Now we can see that we could write this out as a sum over I of vi partial with respect to xj plus a sum over I of that derivative. Now we look at these guys and we realize that they look a lot like matrix vector products. And the reason is because these are Jacobians, right? So these are matrices that have as their rows the outputs, which in this case are the W and the V respectively, and as their columns, they have the indices associated with X. So now we can think about what this must be computing, right? So we have something that looks like a V transpose, and we're going to multiply it by a Jacobian with respect to X of W. Again, rows are outputs, columns are inputs, and so the dimensions make sense here. And we can do the same thing over here. So again, this is a Jacobian matrix, and we need to make sure that that product makes sense. And so when we write this all out, we're going to wind up with something that looks like V transpose multiplied by the Jacobian with respect to X of W plus W transpose multiplied by the Jacobian with respect to X of V. And so this is just writing out these Jacobians as matrices and then observing that these sums correspond to vector matrix products. Now let's take a look at an example. Let's imagine that our function is a quadratic form of the variety that we encounter over and over again in machine learning and statistics. So something like this. Now, if I wanted to take the derivative of this, then I want to break down these pieces into a product just like I did here. So what I could do is I could write these as X transpose Jacobian of mx plus mx transpose times the Jacobian of x. Now, this guy, as we saw just a second ago, is going to be m, and we noticed also that this is going to be identity. And so now we get x transpose m plus x transpose m transpose, which is just what's happening from that, multiplied by identity, so we don't add anything to it, and we see that the answer is going to be x transpose multiplied by m plus m transpose. To finish up, let's look at one example that sort of puts everything together and maps directly onto a least squares regression problem like we might encounter in machine learning. Let's imagine we're going to take the gradient of this with respect to x. So we might do this if we were going to minimize this and try to fit an x with some data. So this is multiplying x by a matrix A, subtracting some b, and then looking at the squared L2 norm of that quantity. If we want to take the gradient of this with respect to x, then we could apply actually a bunch of the rules we've already seen. The first thing we might do is apply the chain rule to this scalar, and we would get, of course, just the norm of ax minus b out front, and then the gradient with respect to x of that norm, right? Now you may recall, just a few minutes ago, we derived the gradient of such a norm. So let's write this back out. So this is, we remember that this is going to be the quantity ax minus b transpose divided by the norm. Remember, we did this just a few minutes ago. And fortunately, these guys cancel, but of course, we need to remember that we need to apply the chain rule again, and we need to be careful about the shape of things. So let's cancel these guys, because that's nice. And we recognize that the Jacobian of this whole quantity is just going to be a, because b doesn't depend on x, and it looks exactly like an example we saw before. So we get, ultimately, then, 2ax minus B transpose multiplied by A. We could have done this a couple different ways if we wanted to. We could have written this out, for example, in terms of the trace, and then we could have multiplied all the terms out and done the derivatives that way. But this takes advantage of just the sequence of steps that we've already looked at in this video and just applies them step by step to get the final answer. And just to complete the story with respect to regression, what we would do if we were trying to minimize is we would set this equal to 0, and then we would solve for x. And what we would wind up with if we sort of multiplied everything out is we can transpose these guys because they're equal to 0. And so we would wind up with something that looked like A transpose AX minus B equals 0. Again, I can do this just because I can transpose 0 without having to think very hard about it. And then I get A transpose A X minus A transpose B equals 0. Or ultimately, A transpose A X equals A transpose B. So this is a normal equation that you'll see in statistics classes and linear regression down the line.